In the last unit, we looked at a variety of models for dynamical systems, and they all have the form an plus 1, the new value, equals an plus delta A, where an was again the old value and delta A was the change. And these models, we were able to use them to say quite a bit about how systems behave. We looked at how we could compute analytical solutions. Sometimes we can find an exact formula for an at every point in time. We looked at find numerical solutions in order to use the computer to try to estimate the value at various points in time. We looked at how we could quantify the long-term behavior by identifying fixed points and classifying their stability. But what we're going to see in this unit is that those types of models, as we've presented them thus far, have some limitations. And the primary limitation that we're going to address is the fact that these are deterministic models. So up to this point, we've assumed that the change was something that was perfectly predictable. That there was a simple rule that told us exactly what was going to happen at each point in time. But that's not necessarily the case. So in this video, we're going to introduce the notion of a random process, and we're going to get into some of the ways that we can use probability to describe solutions to these types of problems, where we're not going to be able to say exactly what's going to happen, but where we might be interested in saying something like, well, what are the different possibilities that could happen, and what are the probabilities of each of those different possibilities? All right, so to start off, let's compare and contrast deterministic and probabilistic models. Deterministic models are one where the outcome is going to be the same every time you analyze the model, right? Everything is perfectly predictable. If you know where the system starts out and you know the rules of the game, then you can determine exactly where it's going to end up. But in the reality, in the real world, there are lots of processes where things behave randomly. And there could be various reasons for this that are mentioned here. For example, in quantum mechanics, we have states of a system which are actually, as physicists best understand, truly random. There are unpredictable things in quantum mechanics that we cannot actually predict. There are other situations where the behavior looks random, but it's actually chaotic. So weather is a classic example of this. Trying to predict what the weather is going to look like a long time into the future is incredibly difficult. And that's due to the fact that weather depends very specifically on the initial conditions. And so if your initial conditions are not completely accurate, your forecast for the future will be inaccurate. And so what you see is weather changes randomly. Our predictions don't work well, and so it seems random to us, but in reality, that's just what's called chaos. All right, another example of randomness occurs when you do things like flipping a coin. Now, there's nothing random about flipping a coin, right? The laws of physics that govern the situation, at least of classical physics, are purely deterministic. So if we were to know exactly the position from which the coin is flipped, exactly its initial velocity, and the motion of all of the particles around it, we could certainly say with certainty exactly whether it's going to come up heads or tails. But for the most part, we don't try to model every factor. And in describing coin flips, the inputs are so complex, it'd be such an involved process to try to model them, that for many problems, it's easier to just treat the outcome as random, recognizing that it's going to come up heads 50% of the time and tails 50% of the time. And so to our eyes, it looks random, when in reality, we just are taking a lot of the details and sweeping them under the rug. Okay? So when we've modeled thus far, we've basically ignored any randomness. We've called them errors or noise, and we've basically said that's the part that we can't actually try to do anything with. And that's where you get deterministic models. But what we're going to do in this unit is we're going to see that we can actually use probability to quantify the noise and say, well, what is the range of values that we expect for the noise? What is the average value of the noise? And what does that tell us about the probabilities of various outcomes from the model? All right, so how do you incorporate randomness into a dynamic model like the ones we've studied thus far? Well, the first thing that you could do is you could have random parameters. So we looked at some examples from banking where we had some fixed interest rate and some payment, and we tried to determine, for example, how much you'd owe on a mortgage or a savings account or some other sort of investment. But if you're thinking about investing in the stock market, then the rates of return actually aren't constant. They change over time, and it can be very difficult to predict what they are. So instead of having a fixed interest rate, you might incorporate a random interest rate, or a random rate of return rather, to describe how the values of your investments will fluctuate over time. All right. Other types of ways we can incorporate this is you may, instead of trying to say exactly what's going to happen, you may try to describe the probability distribution for different outcomes. So in a minute, we're going to look at that rental car model where we had vehicles in Orlando and Tampa, and we'll show how with just a little bit of modification about the way we think of it, we can use it to say not just, well, how many cars are going to be in each place, but what is the probability or the expected number of cars that we're going to have in each place, or what's the probability that a given car is going to be in Tampa or Orlando at a given point in time. Okay, so we can think about our outcomes as being random, and sometimes you can even use deterministic models to describe the probabilities. All right, another example, we looked at these epidemic models where we had people who are susceptible and infected coming into contact with each other. And based on that, we had people switching categories from susceptible to infected. But in reality, those interactions don't occur at regular intervals. There may be random wait times in between those types of infectious contacts. And so we may want to be able to describe that randomness and say what is the expected time between interactions between people and the expected time between transmission of the disease. Okay, so you can imagine changing parameters. You can imagine reinterpreting the variables in the model as probabilities or probabilistic outcomes, and you can imagine having the model itself incorporate randomness inherently. All right, so what this means is when we're setting up models, we're going to still use dynamical systems models, much like the ones before, but randomness is going to become an important factor. And when we want to explore the range of behaviors, what we're often going to do is rely on simulations where we have random variables that show up in our change formula. So we've often been trying to create models for delta A. If delta A has some random component, then we will get different answers every time. And by counting up the number of times various outcomes occur, we can estimate probabilities. And that is what's called a Monte Carlo simulation, where you have a random process and you essentially count up different outcomes. And so we'll look at some examples of that relatively soon.